Hello there and welcome back to our module on probabilities, and we're going to be looking at dependent and independent events. We'll be returning to look at the total probability rule, and we'll start to look at expected values. So our first learning outcome statement here asks us to compare and contrast between dependent and independent events. Let's start with independent events. Knowing the outcome of one does not tell you anything about the probability of occurrence of the other. In other words, the event's occurrence has no influence on the occurrence of other future events. Okay, so think about this like a toss of a coin. Let's say you toss a coin and you get heads, and then you're asked what is the probability on a second toss of getting heads again. Well, of course, it's still 50. Okay, you've got a 50% chance of heads, 50% chance of tails. It is not affected by the fact that you previously tossed the coin and got a head in the previous toss. So, coin tosses, dice rolls as well. So you've rolled the dice once and let's say you get a 4 and we want to know what is the probability of getting a 4 on your next roll. Well, the fact that you got a 4 on your previous roll does not affect the probability of getting a 4 on your next roll. It's still 1 in 6. So we talk about those as being independent events. And notice when we do this, we say the conditional probability of event A occurring given that B has occurred is simply equal to the probability of event A occurring. In other words, event A is not influenced in any way, shape or form of whether event B occurs or not. Now let's contrast that with dependent events. With a dependent event, knowing the outcome of one tells you something about the probability of the other. In other words, an event's occurrence does impact the occurrence of future events. Let's think about lottery balls here. Now, the probability of a ball being chosen is going to change with each pick as the number of remaining balls are reduced. So, for example, let's imagine we're looking at the first pick and we want to know what is the probability of picking a 12 and there's 50 balls in our lottery. Okay, so the probability of picking a 12 is 1/50th. Now, let's imagine the second pick. Let's assume that 12 was not selected in the first pick and go on to the second pick. Now, what is the probability of picking 12? Well, there's only 49 balls left, so it's 1 in 49. Okay, so with a dependent event, the probability is changing based on the outcomes of past events. So, our conditional probability, the probability of event A occurring given that B has occurred, is not equal to simply the probability of event A occurring. Okay, so let's return to our total probability rule here. Now, the LOS asks us to calculate and interpret unconditional probabilities using the total probability rule. Okay, so look, we're looking for the unconditional probability of event A occurring here. So the unconditional probability of event A occurring, and we've been given some conditional probabilities and unconditional. Of course, if you take a conditional probability and multiply it by an unconditional probability, you've got a joint probability. So the unconditional probability for event A occurring is simply all of the joint probabilities where A occurs. Now notice with our unconditional event here, we're calling it S, S1, S2, Sn, okay? If we take our unconditional probabilities and sum them, they have got to come to 1. Okay, let's have a look at an example with our total probability rule. And we did this, covered this in the previous module. We're looking at interest rates increases. We've got an unconditional probability of an interest rate increase of 40%. So no interest rate increase, probability 60%. We've then been given a conditional probability of a recession given an interest rate increase of 70%. And also the conditional probability of a recession given no interest rate increase of 10%. And we're asked overall, what is the unconditional probability of recession? So we're going to be using the total probability rule, but again, I think doing them via decision trees or diagrams is the easiest way to go. So let's have a look. We've got, get a pen up, would help. Okay, so we've got a 40% chance of interest rates increasing and a 60% chance of interest rates not increasing. Okay, so those are our unconditional probabilities, and they will always come first in our probability tree. We then told that if interest rates increase, there is a 70% chance of a recession. So we've now got our conditional probability. 70% chance of a recession given interest rates rise. Now that must be, therefore, equal to a 30% chance of no recession. Remember, our probabilities at each node in the tree have to add up to 1. So, no recession. We're also told in this example that we've got a 10% chance of a recession given no interest rate increase. So again, we can put on recession and no recession. So we've got a 10% chance, 0.1% chance of witnessing a recession given that we haven't seen an interest rate rise, and a 90% chance of no recession given that we haven't seen an interest rate rise. Now, we are interested in the unconditional probability of a recession. So there are two scenarios. You could have an interest rate rise and then a recession, or you could not have an interest rate rise and then a recession. So what we want to look at is the joint probabilities of these two events occurring at the same time. So an interest rate rise and a recession, well, that's going to be 0.4 times 0.7. So that gives us a joint probability of 0.28. So there's a 28% chance that you'll see an interest rate increase and a recession. We also need to analyse no interest rate increase and a recession. So that's 0.6 times 0.1, which gives us 0.06. So there is a 6% chance that you will see no interest rate rise and a recession. So what is the unconditional probability of a recession? Well, 28% chance of recession and interest rate increase, 6% chance of recession and no interest rate increase. Add these two together and we've got our outcome of 0.34%. So there's a 34% chance that we will see a recession, and that is the independent unconditional probability, therefore, of a recession. Now, we could finish our decision tree off as well. Look, there's a 40% chance of an interest rate increase and a 30% chance of no recession. So no recession given an interest rate increase, that's going to come out at 0.12. And 60% chance of no interest rate increase and 90% chance of no recession. So the joint probability of no recession and no interest rate increase is 0.54. Now, of course, if we take these two probabilities, we're getting the unconditional probability of not seeing a recession. Well, if the unconditional probability of witnessing a recession is 34%, then we should see that this comes out at 66%. 0.54 plus 0.12 is indeed 0.66. Now notice if you take all of your joint probabilities, okay, so this one, this one, this one, and this one, and add them together, you will come to 1, okay, because we've got all of the potential outcomes. But here we were asked to calculate the unconditional probability of witnessing a recession, and it is 34%. Okay, and that is using the total probability rule. I find it easier to do it via a decision tree like this, a probability tree like this. I think it becomes very, very obvious at what you're looking at. Okay, so what is the unconditional probability of recession? Well, it is the probability of a recession given an interest rate increase times the probability of an interest rate increase. We saw that. That was our joint probability when we got 0.28 on our decision tree. And it's the probability of a recession given no interest rate increase times the probability of no interest rate increase. And of course, that was our 0.06 or 6%. add the two together, and we've got our 34%. So you certainly don't need to do it with decision trees, probability trees. However, I tend to find that it makes it obvious what I'm looking at, makes the answer more obvious. And certainly whilst you're picking up probabilities, I would certainly recommend sketching them out and labeling them. Right, we turn our attention now to counting rules. Our LOS says identify the most appropriate method to solve a counting problem and analyze problems using factorial combinations and permutation concepts. So the first thing we're doing is looking at labeling here. And it says out of 8 stocks, 4 will be rated long-term hold, 3 will be rated short-term hold, and 1 will be rated as a sell. How many ways are there to do this? In other words, how many different ways can we allocate those 3 labels? Now, to do this, we're going to use n factorial over n1 factorial times n2 factorial times n3 factorial. Okay, so on the top we've got n factorial. That is the total number of stocks. So n factorial is 8 factorial. What is a factorial? Well, 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, a bit long-winded to do that. So you do have a factorial button. If you notice above your multiplication button on a BA2 plus, you have your factorial button. It's an X and a little exclamation mark next to it. Okay, so if we want to work out 8 factorial, what you do is you type 8 into your calculator and then press second function and the multiply button. Let me just get my BA2 plus up to do this. Okay, so if I want 8 factorial, 8, second function, and then the multiply button, and it tells me 40,320. So that top bit of my formula is 40,320. Now my n factorials, n1, n2, n3 are my labels. I've got 3 labels. I've got long-term hold, okay, short-term hold, and I've got sell. So that's why I've got 3 of these. The n is the number of objects I'm going to allocate to each label. So in other words, n1 is going to be 4, n2 is going to be 3, and n3 is going to be 1. Okay, and notice again we are taking the factorials here. Okay, so 8 factorial, we've already said, is 40,320. Let's work out 4 factorial. Okay, 4 factorial and 3 factorial. So 4 factorial is 24. 3 factorial is 6. 3 times 2 times 1. And 1 factorial, that's nice and straightforward. 1 factorial is, of course, 1. 1 times 1. Got to multiply those together. So 24 times 6 times 1 is 144. So our denominator is 144. So 40,320 divided by 144 gives me 280. So there are 280 different combinations of applying those labels to those 8 stocks. When 4 will be hold, 3 will be short-term hold, and 1 will be sell. Right, we're now looking at choosing our objects from n objects. Now when we're choosing, we either choose or don't choose something. We can use combination formulas, okay, and we use combination formula if order is not important. Okay, it's up there, that's the key word here. Order does not matter. Okay, we use combination formulas. What do we mean, order does not matter? Let's imagine we're picking 3 stocks. A, B, and C. Order does not matter if picking stock A first, B second, C third counts the same as picking stock C first, stock B second, stock A third, or stock B first, stock C second, stock A. So any combination here, any combination, doesn't matter which order the stocks are selected, they all count as one choice. Okay, So it doesn't matter the order in which you choose them. So we've got 8 stocks and we want to place orders to sell 3 of them. How many different groups of 3 stocks are there? Okay, so how many different orders of 3 stocks to sell are there if the order in which we choose them does not matter? So to do this, we're going to use this little formula here, n factorial over n minus r factorial times r factorial. N minus r is always the number of stocks not chosen, and r, of course, is the number of stocks chosen. So we've got to label 3 or choose 3 stocks for sale out of 8. So 8 factorial. Well, we did our 8 factorial before, didn't we? 8 factorial is 40,320. We're going to choose 3 for sale, so we don't choose 5. 5 factorial, so that's 5 times 4 times 3 times 2 times 1 is 120. And 3 factorial, 3 times 2 times 1 is 6. Okay, so 120 times 6 on our denominator gives us 720. For 40,320 divided by that is 56. There are 56 different combinations out of those 8 stocks of selecting 3 for sale. When the order in which I select them does not matter. In other words, choosing stock 1, 2, and 3 is deemed to be the same choice as choosing stock 3, 2, and 1. Okay. Now, let's turn our attention to when the order does matter. Now, when the order does matter, then we're saying choosing A first, B second, C third is not the same choice as choosing C second, C first, B second, A first. It's not the same as choosing B second, B first, C second, A third, etc. Okay, they all count as different choices. Now, if they all count as different choices, then the number that our formula produces is going to be higher than the combination formula. So expect the permutation to give you a bigger result. So notice how we do this. We do n factorial over n minus r factorial. So we're doing this exactly the same, but what we're now saying is the order in which we choose these 3 stocks matters. Maybe once we sell the first stock, it affects the marketplace and therefore affects the selling price that we'll get for stock 2 and stock 3. So the order in which we choose these stocks for sale is important to us now. Okay, so 8 factorial over 5 factorial. So that is our 40,320 over 5 factorial. Forgotten what that is. Have to do that on my calculator quickly. 120. So 40,320 divided by 120. And we get 336. Notice 336, if I flip back to the previous slide, okay, when the order did not matter, so the order in which I chose those 3 stocks, choosing stock A first, stock B second, stock C third, was the same as choosing stock C first, stock B second, stock A third. There were only 56 different combinations. When the order of choosing those stocks does matter, then the number of combinations, of course, rises. Now, you should be aware that you can do this on the BAT Plus calculator, so let's have a little look at doing that. So exactly the same computations. If you notice above your plus button on your BAT Plus calculator, you will see NCR for combination. And if you look above the minus button, you'll see NPR for permutation. So if we want to choose 3 from 8, what you do on your calculator is you type 8, second function plus, then 3, the number of items you want to select, then press equals, and you should see 56 appear on your screen. Okay, let me get my BAT Plus up and just take you through the button presses. So 8 first of all, second function plus button. I want to choose 3 items. How many combinations? 56. Okay, if we want permutations, then we do exactly the same, but we type the NPR button, which is, of course, second function and the minus key. So let's do that now. 8 items to choose from, second function minus. I want to choose 3, and there you go, 336.